Today we are going to look at Introduction to Design in Timber to BS 5268. This is George Kamiti. Welcome to our channel and please don't forget to subscribe. Design of timber elements is normally carried out in accordance to BS 5268 and the following sections will be outlined based on the contents of the code. This includes the stress grading, the grade stress and strength class, and the permissible stresses. Beginning with stress grading, the strength of timber is a function of several parameters, including the moisture content, density, size of the specimen, and the presence of various strength-reducing characteristics such as the knots, the slope of grain, fissures, and wane. We have two timber visual grades, which include the general structural, which is denoted by GS, and the special structural, which is denoted by SS. We also have four machine grades, which include the MGS, MSS, M75, and M50. Let's begin with grade stress and strength class. Table 6.1 shows typical timber species stroke grade combinations and associated grade stresses and moduli of elasticity. This information from Table 6.1 would enable the designer to determine the size of a timber member given the intensity and distribution of the loads to be carried. This is Table 6.1 showing grade stresses for softwoods graded in accordance with BS 4978 for Service Class 1 and Service Class 2. Table 6.2 on the other hand shows softwood combinations of species and visual grades which satisfy the requirements for various strength classes. Then from there we are going to look at strength classes. There are a total of 16 strength classes which include C14, C16, C18, C22, C24, C26, C27, C30, C35, C40, D30, TR26, D40, D50, D60, and D70, with C14 having the lowest strength characteristics. The strength class designations indicate the bending strength of the timber. Strength classes C14 to C40 and TR26 are specifically for softwoods, and the strength classes D30 all the way to D70, those are for hardwoods. The strength class TR26 is intended for use in the design of trussed rafters, thereby the designation TR, trussed rafters. The third element that we are going to consider is the permissible stresses. The grade stresses given in Table 6.1 and 6.3 were derived assuming particular conditions of service and loading. And in order to take account of the actual conditions that individual members will be subject to during their design life, the grade stresses are multiplied by modification factors, which are known as K factors. The modified stresses are termed as permissible stresses. BS 5268 lists over 80 K factors, but however, the following subsections considers only those modification factors which are relevant to the design of simple flexural and compression members. And these K factors include the following. We have K2, which is the moisture content factor. We have K3, which is the duration of loading factor. We have K5, which is the notched ends factor. K7, the depth factor. We have K8, load sharing systems factor. And K12, the compression member stress factor. So those are a number of 6 K factors that we shall be using in our design in this topic. Then from there, we are going to look at the moisture content factor, which is K2. The strength and stiffness of timber decreases with increasing moisture content. This effect is taken into account by assuming timber used for structural work to a service class. And BS 5268 recognizes 3 service classes, which include, we have service class 1, service class 2, and service class 3. Starting with the service class 1. This service class 1 is characterized by a moisture content in the material corresponding to a temperature of 20 degrees Celsius and the relative humidity of the surrounding air only exceeding 65% for a few weeks per year. Timbers used internally in a continuously heated building normally experience this environment. And in such environments, most timbers will attain an average moisture content not exceeding 12%. So that is service class 1. Going to service class 2. Service class 2 is characterized by a moisture content in the material corresponding to a temperature of 20 degrees Celsius and the relative humidity of the surrounding air only exceeding 85% for a few weeks per year. And timbers in covered buildings will normally experience this environment. In such environments, most timbers will attain an average moisture content not exceeding 20%. Then the third class is service class 3, and in this class, due to climate conditions, it is characterized by higher moisture contents than service class 2, and it is applicable to timbers used externally and timbers which are fully exposed. Table 6.4 shows modification factors K2, by which stresses and moduli for service class 1 and 2 should be multiplied to obtain stresses and moduli applicable to service class 3. Then we go to K3, that is the duration of loading factor, K3. And in this factor, the stresses given in table 6.1 and 6.3 apply to long-term loading. But where the applied loads will act for a shorter duration of time, e.g. snow and wind, the grade stresses can be increased further. And table 17 of BS 5268, which has been reproduced in this book as table 6.5, gives the modification factor K3 by which these values should be multiplied for various load combinations. Then we go to K5, that is the notched ends factor. And notches at the ends of flexural members will result in high shear concentrations which may cause structural failure, and therefore they must be taken into account during design. And in notched members, the grade shear stresses parallel to the grain, that is table 6.1 and 6.3, are multiplied by a modification factor K5 calculated as follows. For a notch on the top edge, the K5 is given as shown on that formula. And for a notch on the underside, the K5 is given by HE divided by H. Clause 2.1 0.4 of BS 5268 also notes that the effective depth, that is HE, should not be less than 0.5 H. That is, K5 should be greater than or equal to 0.5. Then the fourth K factor is the depth factor, that is K7. And in this case, the grade bending stresses given in table 6.3 only apply to timber sections having a depth H of 300 millimeters only. For the depths of beams, the grade bending stresses are multiplied by the depth factor K7, which is defined as given by the underlying formulas. Then number 5, we have load sharing systems, that is K8. And the grade stresses given in tables 6.1 and 6.3 apply to individual members, e.g. isolated beams and columns, rather than assemblies. When 4 or more members, such as rafters or joists or wall studs, spaced a maximum of 610 millimeters, center to center, act together to resist a common load, the grade stress should be multiplied by a load sharing factor, K8, which has a value of 1.1. Therefore, K8 is taken as 1.1. Number 6, that is the compression members, K12. The grade compression stresses parallel to the grain given in tables 6.1 and 6.3 are used to design struts and columns. These values apply to compression members with slenderness ratios less than 5, which would fail by crashing. Where the slenderness ratio of the member is equal to or greater than 5, the grade stresses should be multiplied by the modification factor K12 given in table 22 of BS 5268, which is reproduced in this book as table 6.6. Then from there, we are going to look at now the timber design. And in timber design, the following sections will be considered in the design of flexural members, compression members, and stud walling. When we have the symbols, and for the purposes of timber design, the following symbols will be used. We have symbols of geometrical properties, and these symbols include the breadth of the beam, depth of the beam, total cross-section area, radius of gyration, second moment of area, and elastic modulus. Then we have the symbols for bending, we have the symbols for deflection, we have the symbols for shear, we have the symbols for bearing, and we have the symbols for compression. So those are the symbols that we shall be using in this topic. Then from there, we are going to look at the flexural members. We know that flexural members include the beams, rafters, and joists. And all calculations relating to their design are based in the effective span and principally involves consideration of the following aspects which are discussed below. Number 1 is bending, number 2 deflection, number 3 lateral buckling, number 4 shear, and number 5 bearing. Generally, for medium span beams, the design process follows the sequence indicated above, that is bending, deflection, lateral buckling, shear, and bearing. That is the sequence of design process of medium span beams. However, deflection is usually critical for long span beams and shear for heavily loaded short span beams. Beginning with the bending, which is the first step, if flexural members are not to fail in bending, then the design moment M must not exceed the moment resistance, that is MR. The design moment is a function of the applied loads. We should know that. The moment of resistance for a beam is given by permissible bending stress parallel to the grain multiplied by section modulus. And for rectangular sections, the section modulus is given by BD squared divided by 6. The permissible bending stress is calculated by multiplying the grade bending stresses by any relevant K factor. For a given design moment, the minimum required section modulus can be calculated using the following equation. That is, The required section modulus is given by bending moment, the design bending moment, divided by the permissible bending stress parallel to the grain. A suitable timber section can then be selected from tables NA2, NA3, and NA4 of BS EN 336. That is structural timber sizes permitted deviations. These tables give the commonly available sizes of respectively sawn timber, timber machined on the width, and timber machined on all the four sides. Table NA2 is reproduced here as table 6.7, that is in our book. Table 6.8 is an expanded version which includes a number of useful section properties to aid in design. Finally, the chosen section should be checked for deflection, lateral buckling, shear, and bearing to assess its suitability. Then we go to step number 2, that is deflection. Excessive deflection of flexural members may result in damage to surfacing materials, ceilings, partitions, and finishes, and to the functional needs as well as aesthetics requirements. Generally, such damage can be avoided if the total deflection of the member when fully loaded does not exceed the permissible deflection. The permissible deflection is generally given by 0.003 times the span. But for longer span domestic floor joists, that is spans over 4.67 meters, should not exceed 14 millimeters. The total deflection is the summation of the bending deflection plus the shear deflection. Therefore, total deflection is equals bending deflection plus shear deflection. Table 6.9 gives the bending and shear deflection formula for some common loaded cases for beams of rectangular cross section. Then you go to step number 3, that is lateral buckling. If flexural members are not effectively laterally strained, it is possible for the members to twist sideways before developing its full flexural strength, thereby causing it to fail in bending, shear, or deflection. This phenomenon is called lateral buckling, and it can be avoided by ensuring that the depth to breadth ratios given in table 6.10 are complied with. Then you go to step number 4, that is shear. If flexural members are not to fail in shear, then the applied shear stress parallel to the grain should not exceed the permissible shear stress. For a beam with a rectangular cross-section, the maximum applied shear stress occurs at the neutral axis, and it is given by 3FV divided by 2A, where FV is the applied maximum vertical shear force and A is the cross-sectional area. And the permissible shear stress is given by grade stress multiplied by appropriate K factor. Then we go to number 5, that is bearing perpendicular to grain. Bearing failure may arise in flexural members which are supported at their ends on narrow beams or wall plates. Such failures can be avoided by ensuring that the applied bearing stress never exceeds the permissible compression stress perpendicular to the grain. The applied bearing stress is given by F, which is the bearing force, divided by B, that is the breadth of the section, times the bearing length, which is LB. The permissible compression stress is obtained by multiplying the grade compression stress perpendicular to the grain by the K factors for moisture content, load duration, and load sharing as appropriate. It should be noted that the grade compression stresses perpendicular to the grain given in tables 6.1 and 6.3 apply to bearings of any length at the ends of the members and bearings 150 millimeters or more in length at any position. So ladies and gentlemen, that is the introduction to timber design to BS 5268. Don't forget to subscribe to our channel. Thank you.